In the coming clips, we will look at functions and means to approximate those functions by certain polynomials, so-called Taylor polynomials. And the main motivation lays in the fact that we can speak of tangency of graphs. The more the derivatives of functions agree, the more the polynomials may be used as approximations for those functions. That will amount to the Taylor's theorem that we will prove later on. So, as a starter, we need to define tangency. Let's consider two functions on an interval I, let's say f and g. These are real valued functions, and suppose we have an a in that interval. Then the graphs of f and g are called to intersect for x equals a if only the images are the same. So the function values in a are equal. Moreover, we'll say that the graphs of f and g are tangent for x equals a if not only the function values are the same, but also the first order derivatives. Yeah, of course, this will need the derivatives to exist, right? Okay. So as an example, look at the following three functions. So we have fx equals 2 minus e to the power x minus 1. G0 is the constant function 1, and G1 is the linear function 2 minus x. Then we may calculate it's straightforward work to calculate the following derivatives. The derivative of G0 is 0 and G1 prime equals minus 1. Then we see the following, that if we plug in the element 1 in the functions, then we get as a function value for all three functions f, g0 and g1 the value function value 1. If we then calculate the derivatives, we see that the derivative in for f in 1 equals the derivative of g1 in 1. They equal minus 1. However, g0 prime is 0, of course, since it's a constant function. Okay, the conclusion therefore is that if we look at the graphs of f, g0 and g1, then these all intersect for the value a equals 1, and the graphs of f and g1 are tangent at a equals 1. The graphs of f and g0 are not tangent. So we can speak of order of tangency. Suppose that we have two functions. Let's say we have two functions defined on an interval, right? And that we can, well, the a is an interior point of the interval. Then we will call the graphs of these n times differentiable functions. Yeah, we will assume that we can take derivatives in a n times. Then we will call the graphs of f and g tangent in x is a to the order n if the function values are the same, the first order derivatives are the same, the second order derivatives are the same, just to the nth order derivatives are the same. Then these graphs are called tangent in x is a to the order of n. So for example, here we have the old candidates. So here we have the constant function, the graph of the constant function g0, and we have the linear one, g1 is that one, the yellow, the one with the yellow graph, and we also have the green graph, which is a newly defined function g2, which is 3 over 2 minus 2x minus a half times x squared. Then what we see is that g0 is only intersecting the graph of f. g1 is also tangent to the order 1 with the graph of f. At G2, and G2 we can see that also the second order derivative of G agrees with that one of f in 1. This means that G0 only agrees with the function value in f0, G1 with the function value and the derivative in 1, and G2 matches not only the function value, not only the first order derivative, but also in the second order derivative, which means that the curvature of G2 around 1 is almost the same as that one of f.